Suppose I have this graph. Now, the first question, what kind of graph is this? Snapshot graph or a history graph? The information that tells us is what am I plotting it against. This is position, so this must be a snapshot graph. It's a picture of the entire wave. So this might be some weird pulse on a string. So I've whipped the string, causing this weird pulse. Now I've got it very angular, which is not realistic, but it's the sharp angles will help us in trying to understand snapshot graphs and how to create history graphs from them. Okay, so imagine this is some pulse on a string. I've whipped the string and it's traveling along. I've indicated the direction of the velocity, and I'm going to go ahead and say that this is in meters here, and I'm going to say that this is traveling at 1 meter per second, okay, to the right. So I've indicated the speed and the direction, and I've got the units along this x-axis. My question is, how do I create a history graph? So first thing, for a history graph, I need to know what point I'm looking at. So I'm going to talk about first this point, point 3. So I want to create a history graph. Okay. And I'm going to have the seconds marked out here. 1, 2, 3, 4, 5, 6, 7. Okay, these are units of 1 unit, so 1, 3, 5, 7. Okay, and this is the displacement, so my vertical axis is just the same. And I want to know what is happening. This is a graph supposed to describe x equals 3. X equals 3 meters to be more precise. How do I create that? Well, there's a bit of information I need to know here. Now, I kind of assumed, but I'm going to make it explicit. I need to know what time this is at. This is the entire string at some time. To make it easy, let's go ahead and just choose t equals 0. So this is a picture of the entire string at t equals 0. Okay? And that pulse is moving to the right at 1 meter per second. So let's populate this graph now by using these bits of information. So at t equals 0 seconds, what is happening to the piece of string that is at x equals 3? Well, at t equals 0 seconds, I can see it. It's at the equilibrium line. It's not doing it. There's no displacement. So at t equals 0, it is 0. Okay? Now, 1 second later, what's happening to this? Well, to understand that, I need to know where is this 1 second later. This is at t equals 0. To find that out, I know that it is moving 1 meter per second to the right. So that means if I take a look just at this leading edge right here, this leading edge, 1 second later, moving 1 meter per second, it's at 1 meter, which means 1 second later it's going to be 1 meter further, or at 2 meters. So 1 second later, this leading edge is right here. Okay, so I can draw a little dot, and then I can consider every other point along this and see that that pulse has moved forward 1 meter. Every piece of it has moved forward 1 meter. So at t equals 1 seconds, the point at x equals 3 still isn't moving. So still there at equilibrium. Alright, 1 more second later at t equals 2 seconds. Where is it? By the same argument, we could draw it again, and I can see that now this leading edge has just barely gotten to 3. It's just barely gotten to that point. Okay, and the rest of the wave is followed, so I can, draw another set of dots, and it's just barely gotten there. So at t equals 2 seconds, it's still at equilibrium, but I know something's going to happen. I know it's going to start rising. Okay, now to figure that out, let's go ahead and jump to t equals 4 seconds. Sorry, t equals 4 seconds, right? I apologize, 3 seconds, and see what's happened. Well, this leading edge is now at 4 meters, and this corner here, which was at 0, 3 seconds later is now at 3. So that wave is now like that. It's sitting there. And so the piece at 3 meters has jumped up to this height. We can just have a standard height here. Okay, it's jumped up to that height. And so at 3 seconds, it is now like that. Okay. Well, how do I connect those dots? Is it just a straight line? in this particular case it is, but let's see more specifically why. What about at 2.5 seconds? Okay, at 2 seconds, this leading edge had moved 2 meters. At 3 seconds, this leading edge had moved 4 meters, and this corner had moved, 3 meters. It moved 3 meters, so it was there. Well, what is at x equals 3 at 2.5 seconds? Okay, well that means this leading edge is gotten to right there. Okay, at that point between 3 and 4 meters, which means what is at 3? Well, the corner is at 2.5 meters. This corner has gotten this far, which means that halfway up, this point right here has gotten to 3 meters. And so I know over there at 2.5, I'm halfway up this line. And I could keep doing that for every piece of this pulse. And I can then connect those lines like that, and I know it's doing that. Okay. Now you could keep going and consider other pieces at 1 second later, at 4 seconds. Well, what's at 3? This point here at -1 has moved 1, 2, 3, 4 in 4 seconds, which is at 3. So it's right there. This trailing edge will get to that 3 in 5 seconds. Since it's moving 1 meter per second, it's 5 meters away. So 5 seconds gets to 3. So it's right there. And that's this trailing edge here, which immediately drops down. And so at times after that, it's at 0. So I know it's going to look like this. And so I can connect all those dots, and I've got the entire history graph for x equals 3 to look like that for these specific times. And let me give a unit there for seconds. So it's interesting to note that the pulse looked like this on the snapshot graph, and it looks a mirror image of it on the history graph. Now, because of where the leading edges were and the time, it's not necessarily symmetric about the 0 of time, but it's just as if it's flipped, and we have to figure out where that leading edge is. And very often, if the wave is moving to the right, you know that these two graphs are going to be mirror images of each other. Whereas if the graph is, or if the wave is moving to the left on our standard coordinate system, then these will actually be the same picture, shifted depending on what time we're talking about, but they'll be the same picture. Okay, to emphasize that, let's try another point. What is going to be the history graph? Okay, I'm going to draw these same units. Okay, those same units there. At x equals -3. What would it be like? What would it be like? So using that same logic, I'll go a little bit quicker this time. Is the leading edge is now right here. Oh, sorry, I failed something. So what is it at -3? Well, if the wave's moving this way, it's going to be 0 for all future times. But what if we switch it, and this is now the wave is moving. The wave is moving to the left. So we got our 1 meter per second, but it's moving to the left now. Okay, so this wave is moving for the left as we consider that point. So if that's true, the wave is moving this way. Then 1 second later, this trailing edge has gotten to here, and this point at -3 snaps up to the maximum amplitude right away. So it's 0 at 0 seconds, because we can see it. Then it snaps up at 1 second. Okay, and then this point will get to it 1 second further. This point will get to it a second after that, and we can get the graph to ultimately look like that, and then continuing on. So that would be the history graph if this wave were moving to the left at 1 meter per second, considering the point x equals -3 meters. And we can see that it is an identical shape, shifted because of what time we start at and where the leading edge is at relative to the point we're considering. But mirror image if the wave is moving to the right, and same image if the wave is moving to the left.